Hello. Thank you for being here. I'm going to meet you, all of you. Thank you for being here for another one of our lectures. Today we'll be going over section 6.2. So let's go over our new section, which in comparison to our Thursday lecture, which was super long, I think today will be pretty short. We're going to go over 6.2, and since we have an idea of factoring and we work with 6.1, it's just an extension of it. It should be relatively simple if 6.1 was something you understood. From there, I'll answer any homework questions at the end. And that's it for today. And thinking for Thursday, maybe I'll record my lecture so that you don't have to sit in live. So that's something I'm considering doing for our Thursday meeting. Maybe that way we can only meet once a week or something along those lines. All right, so let me go ahead and share my screen. So let's continue with 6.2. Now, like I said, 6.2, it's a lot like 6.1. It's just we're adding to it. And that's what each section in this chapter is. It's the same idea, but we're adding another concept to what we learned already. All right, so 6.2 is going to be dealing with 3 different types of different equations. The main difference is, if we recall from 6.1, they're all the same. They're all either cosine, sine, secant. And if there's more than one trig function, say like we have, like here, you see how you have tangent and tangent? We might deal with examples, and here we have secant and secant. We're going to deal with examples where it's not the same trig function written for each term. So that's what we're going to learn in this section, how to go about it. Okay, 6.2, more techniques for solving trig equations. Sometimes the trig equation is not yet ready to be solved. This can occur when 1, the equation contains 2 or more different trig functions, or 2, there is more than one argument present, such as not an x, but like a 2x. In either case, we prepare the equation by using one or more trig identities to alter the look of the equation. And the next few examples demonstrate this technique. All right, so before we begin, make sure you have these 2 things handy. Make sure your unit circle. That's something that never goes away, so make sure you have it handy. And 2, have handy your 5.4 and your 5.1, that initial page that has all of the formulas there. That's going to be helpful. We're going to be dealing with those type of equations. Well, pretty much everything we learned in chapter 5. Okay, let's work on example 1. Solve for x when x between 0 to pi for 2 cosine of x plus 1 equals secant of x. So the problem here is secant and cosine, they're not the same trig function. So I want to write it with either all of them being cosine or all of them being secant. I can't work with different trig functions. So how will we go about it? Let's look at our procedure. This equation contains 2 different trig functions. Fortunately, we can write secant as 1 over cosine, right? Secant is a reciprocal of cosine. All right, so let's make that change. Let's write secant as 1 over cosine. Okay, now we're in good shape because everything is written in terms of cosine. That's something I can work with. Now, we are not too happy, or at least I'm not so happy about having this fraction. So what can I do to get rid of that fraction? Well, because I have an equal sign, and equal signs are very powerful, I can multiply the same thing to both sides and not lose the value of it. So next we're going to multiply each side by cosine. All right, so I'm going to multiply this side of my equation by cosine of x and this side by cosine of x. All right, if I do, I have to multiply it in, and here I have to distribute it to each term. So that I have cosine times 2 cosine of x gives us 2 cosine squared x. Cosine times 1 gives me cosine. And 1 over cosine times cosine, they cancel, we're left just 1. Okay, now whenever you work with an equation that's a quadratic, you have to set equal to 0. The left side is a quadratic in form. It must be set equal to 0. Move the constant term to the left side. So we go ahead and just subtract one of both sides. Minus 1, minus 1. All right. Once we do that, we're left with the type of problem we learned in 6.1. So now we can go ahead and we can factor. So this is where, if you'd like to, you can go ahead and change it to let w equal cosine of x. You can replace cosine with w and cosine squared with w squared. And you can work with 2w squared plus w minus 1 is equal to 0. And you can factor. Let's go ahead and factor. Let me do it right here on the side. Oh, we have it here. Factor left side, and if it's so, you can always substitute. So that factor should be 2w minus 1 and w plus 1. Let's go ahead and change w with cosine. So that we have 2 cosine of x minus 1 and 2 cosine of x plus 1. We set each one equal to 0, and we're left with our two answers. X is equal to pi over 3 and 5 pi over 3. And our other one, our pi. We write them all together. Let's go ahead and do example 3. Let's go ahead and solve for tangent of x minus 3 cotangent of x. Go ahead and give this one a try. I'll give you about 2 minutes to get started. Now the idea is you want to have the same thing for each term. So the fact that I have a tangent and a cotangent is a problem. So is there a way where I can make both of them either tangent or maybe cotangent? Go ahead and do example 3. I'll stop you at 221. Okay, let's go ahead and work this out together. I gave you a moment to try to attempt this one on your own. I wrote that first line. So we see that we can change cotangent to 1 over tangent. All right, because I have an equal sign and because we don't want fractions, we can go ahead and multiply both sides by tangent of x. Now, why are we doing this? We're doing this because we have a 1 over tangent of x. And we know that if we multiply by a tangent of x, that would make it cancel. So your hopes are to get rid of that fraction. All right, now let's multiply. I have to multiply my tangent of x to what I have on the inside, which is tangent of x minus 3 over 1 tangent of x equals 0, and I also multiply tangent of x to the other side. Okay, well, 0 times anything is 0, so I have equals 0 the other side. And here I'm left to multiply. So tangent times tangent gives me tangent squared x. And then I have negative 3, and tangent over tangent gives me 1. So it's just the 3. Let me write it a bit better. I have tangent squared of x minus 3 is equal to 0. All right, we can work with that. Let's go ahead and solve. If we solve, we're left with, we can move the 3 over. So plus 3 plus 3. I'm left with tangent squared of x is equal to 3. I want tangent squared. I have tangent squared and I have tangent. I have tangent squared and I want tangent. So let's take the square root of both sides. Remember, plus or minus. So I'm left with tangent of x is equal to plus or minus the square root of 3. And that's our answer. Our answer is tangent. Oh, no, we have to figure out what it is. So when is tangent equal to square root of 3? And I want positive and negative. So take a look at a unit circle. And you see that tangent gives you square root of 3 at every 60-degree mark. So everything I had is 60. So I have radian measure. We'll use radian measure. So I want our answer to be x is equal to, well, what is tangent? 60. Tangent is 60 at pi over 3 at 2 pi over 3. 4 pi over 3 and 5 pi over 3. Now remember what I'm saying by 60 is if you have your unit circle, you want that 60-degree mark. That's the one we're using as a reference. That's why you have those 3 tick marks. The first tick mark is 30, 45, and 60. And if you look at unit circle, you have also written radian measure. In this next example, we use Pythagorean identity to prepare the equation for solving. Example 4, solve for x when x is between 0 and 2 pi for 4 cosine squared minus 4 sine x minus 5 equals 0. So we have the same problem here. I have a cosine and a sine. And I want to have the same trig function. I want to have all sines or all cosines. So I have 2. Now, what can I do to change one or both of them so they're the same? Well, that cosine square, and because we see a square, is a big hint as to what we can do. Well, we know from our Pythagorean identity, we know that cosine squared is 1 minus sine squared, right? So we're going to use that to our advantage. So I can replace my cosine squared with 1 minus sine squared. All right, so we're going to replace cosine squared with 1 minus sine squared, and that fixes our problem. Now I'm left with only sines. Okay, great. Now I'm left to distribute what's outside of my parentheses. So 4 times 1 is 4, minus 4 times negative sine squared gives us minus 4 sine squared. And I rewrite my problem. Minus 4 sine of x minus 5. Combine like terms whenever possible. And I see I have a 4 and a minus 5. Gives the negative 1. Okay, now we have all signs. Now, if you'd like to, you can go ahead and continue using your substitution. Instead of sign, you can write a w, so that you have 4w squared plus 4w plus 1. If you'd like to see your factoring written down, your steps, you have 4w squared plus 4w plus 1. Remember, you multiply your a and your c. 4 times 1 is 4. Your goal is to replace it with, find two numbers that replace your middle term. So what two numbers multiply to 4 but add to give you 4? 2 and 2. So this factors to be 4w squared plus 2w plus 2w plus 1. Then you can factor your first two terms and your last two terms. Your first two terms have a 2w in common. So we're left with 2w plus 1. And our last two do not have anything in common, so I can write a plus 1 placeholder. So I have w plus 1. And so this factors to be 2w plus 1 and 2w plus 1. So we get the same thing twice. All right, let's replace w with sine so that we are now here. All right, so let's go ahead and solve. So I'm left with 2w plus 1, and because it's the same thing, you can do it just once, right? Or if you write it as a square, you see a square doesn't matter because you have a 0. Okay, if we solve for x, we subtract 1 on both sides, we divide by 2. We're left with sine is 1/2, negative 1/2. So when is sine negative 1/2? Sine is negative in quadrants 3 and quadrant 4. So then we're left to see in quadrant 3 and 4 where sine is 1/2. And we see the sine is 1/2 in 7 pi over 6 and 11 pi over 6. Now my biggest question to you is, does anyone have a question as to how we get from this to this? Everyone okay? I'm going to take your silence as a yes or okay. All right. One other thing we can do. So what have we learned so far? We learned that we need the same trig function in an equation. We can't have a mixture of it. They need to be all cosines, all sines, all tangents, all cosecants, secants, and cotangents. And we learned two tricks to do it. One of them is we can replace by the reciprocal if that's an option. Sometimes it might not be an option, but we saw that with tangent and cotangent, we saw with secant and cosine. Another option is to use your Pythagorean identities. That might be an option. So we're gonna add one more to our list. And that's this part of our section, our double angle identities. Let's continue with our text. If the equation contains two different arguments, then we must find a way using an identity to change one of the arguments to be like the other. For example, if an equation contains either sine 2x or cosine 2x, we can use a double angle identity to write the function with an argument of just x. So let's see an example. Solve for theta when theta is between 0 and 360. So I'm going to note to myself in degrees. So that sine 2 theta is equal to square root of 2 cosine theta. All right, the problem here is two of them. One of them is, you see you have sine and cosine. They're different. That's the problem. Another thing we need to be aware of is that 2 theta. That changes our argument. All right, so let's go ahead and see how to work this out, our procedure. This equation contains two different trig functions and two different arguments. The most pressing concern is for the two arguments. So use a double angle identity for sine to simplify the left side. So this 2 theta looks familiar, right? I believe that's from section 5.4, our double angle identities. I can replace that. Now from my double angle identities, this can now be written as 2 sine theta cosine theta. All right, now I'm left to work with our equation, but now we see that we need to set it equal to 0, so we make it equal to 0. And now we're left with our problem here. 2 sine theta cosine theta minus square root of 2 theta equals 0. Now what can we do here? We have a mixture of sine and cosine. So what can we do? Well, what makes this one different is that we're not adding and subtracting that cosine. It's being multiplied. So hopefully we can factor, and we can work with two different, we can think of them as sub equations. So we see we have cosine on each one. So let's factor our cosine theta. If we factor cosine theta, what are we left with? We're left with 2 sine theta minus square root of 2. Okay, now by product rule, we can set each one separately equal to 0. So that I have cosine theta is equal to 0, and 2 sine theta minus square root of 2 equals 0. Now that's okay. I know you might be thinking, hey, what's going on? We have a mixture of cosine and sine. What makes this okay is that it's not being added nor subtracted, meaning the different trig functions. Because it is being multiplied, we can hopefully be able to factor so that we can write each factor equal to 0. All right. So we're here. Now when it's cosine 0, you take a look at your unit circle. It's 0 at 90 and at 270. We have a bit more work to do for our second one. 2 sine theta minus square root of 2 equals 0. So I add square root of 2, add square root of 2, divided by 2. We're left with sine equals square root of 2 over 2. So when is sine positive? Square root of 2 over 2. That's in quadrants 1 and 2. So we have 45 and 135. So together we get these answers. All right, before we leave today, we'll do a problem like this in our homework. All right, caution. In example 5, in the second step, we had 2 sine theta cosine theta equals square root of 2 cosine theta. There might be a temptation to divide each side of the equation by cosine theta. However, division by 0 is never allowed, so it is unwise to divide an unknown value or quantity if it might be 0. In this case, if we did divide out the cosine theta, we would lose two solutions, 90 and 270, and the solution set would be incomplete. So lesson learned is do not divide by your trig function because you're losing that value and thus losing a potential answer. All right, here's an argument type of question. Sometimes we can use a double angle identity even when no other function is present. In section 6.4, we'll learn to make first solving sine of 2 theta without using a double angle identity. All right, so this is where we have the arguments. We'll learn that, I think, in our next section. Let's do example 6. Solve all possible degree values So all answers, remember that's going to write plus k and z of sine 2 theta equals 0. Use the double angle identity for sine. So because we have that 2 theta, that's a problem. The way we're going to go about it for this section is we're going to rewrite it using our double angle identities. Okay, so we can write sine of 2 theta. If you look at your identities from section 5.4, we see we can rewrite this to be 2 sine theta cosine theta. All right, they're being multiplied, so I can go ahead and split it. So we have 2 sine theta equals 0 times cosine theta. And when is sine equal to 0? At 0 and 180. When is cosine equal to 0? At 90 and 270. Almost done. Because we want all possible values of theta, we add up 360k to each one of these. So we write down each answer separately and write 360k, where k is an integer. However, be careful. However, because the solution occurs every 90 degrees, we can abbreviate this by adding 90k to any of the first value of 0 plus 90k. Even better to write it just as 0 equals, not 0, theta equals 90k, where k is contained in z. So what's saying is 90 degrees. You see 90 and 180? Well, mainly 90. 90 happens here, and it would repeat also here for when cosine is equal to 0. So it's saying if you want to write less, you can go ahead and change it because you see that those answers repeat. But if you don't catch it, that's not a major worry. In this next example, the equation contains the arguments of both 2 theta and theta. It is cosine 2 theta that must be written, but there are 3 identity options. So remember, for double angle identities, we have cosine of 2 theta equals cosine squared minus sine squared. We also have 1 minus 2 sine squared, and we have 2 cosine squared minus 1. So how do you know which one to pick? It depends on what you're given, right? So let's take a look at example 7. Solve for theta when theta is between 0 and 360. I'll write a note that's in degrees. For cosine of 2 theta plus 3 sine theta minus 2. So as you're working through this problem, what would be the best option? Well, I see that I can replace my cosine 2 theta. Because if I replace it, I will be left with sine. Why don't we choose this option? That way I can have all sines. All right, let's go ahead and do that. So that we're going to replace cosine 2 theta with a 1 minus 2 sine squared theta plus 3 sine theta minus 2 is equal to 0. All right, it's adding, so we can just drop our parentheses. So I have 1 plus 2 sine squared theta plus 3 sine theta minus 2 is equal to 0. All right, let's go ahead and combine like terms. I have a 1 and a minus 2. We get negative 1. So I have negative 2 sine squared theta plus 3 sine theta minus 1 is equal to 0. All right, so I don't know about you, but having a negative 1 is not ideal for me. I don't like it. Because I have an equal sign, I can go ahead and divide out my negative 1. So it just causes a sign change. So that we now have positive 2 sine squared theta minus 3 sine theta plus 1 equals 0. And you don't have to do that. It's just something that is a preference thing. All right, let's go ahead and solve. Now, the main problem here was which one of the three identities do we want to work with? And we chose the one that has a sign. Now we're left to go ahead and solve. So we have to go ahead and use substitution. So let's say W is equal to sine theta. If so, we're left with 2W squared minus 3W plus 1 is equal to 0. Okay. So what factors of 2 add up to -3? -2 and -1. Let's replace that middle term with -2W and -1W. So I have 2W squared minus 2W minus W plus 1 is equal to 0. Let's group our first two and our last two so that we have a 2W we can factor. So we're left with W minus 1. Now, we want the same thing in the parentheses, but it's a bit off. Let's factor -1 so that I have W minus 1. So this factors to be 2W minus 1 times W minus 1 is equal to 0. All right, let's replace it back with a sine theta so that we have 2 sine theta minus 1 is equal to 0. And W sine theta is equal to 0. All right, so this gives us plus 1, we divide by 2. Sine theta is equal to 1/2, and sine is equal to 0. Okay, we get that sine is 1/2, positive 1/2. So we're in quadrants 1 and 2. It's positive 1/2 at 60. No, at 30 and at 150. 30 and 150. And sine is 0, which is y, at 0 and pi. Or not pi, we want 180. Our answers in degrees, and these are our answers. Theta is equal to 30, 150, 0, and 180. That's a lot of work, but that's okay because we know how to develop each part. All right, last little piece, squaring each side of a function. So I don't know if you recall this from your college algebra courses or algebra courses, where you can have answers that are extraneous, meaning that, yeah, your work is correct, your algebra is correct, but when you check your answer, you see they get a false solution. This happens when we're just working with radicals and we square both sides. So that's something you need to be careful of. Squaring each side of an equation is a technique used in algebra for solving equations by a variable within a square root, such as square root of x plus 3 equals x plus 1. To solve this equation, we start by squaring each side as shown here. So here it shows the work. We see that square root's a problem, so let's go ahead and square it. We squared, and we got our answers to be 1 and -2 after some work. Now, once we go ahead and we verify our work, we see that we get a true statement, but it might so happen that sometimes you get a false statement. What we discover is the equation is true for x equals 1, but not true when x is equal to -2. So there is only one solution. The side of a solution, -2, is called an extraneous solution, and it occurs because the squaring process actually gives us a different equation to solve, one with more possible solutions than the original equation. This technique of squaring each side can be helpful in solving some trig equations. We might use this option when there appears to be no trig identity available. Squaring each side of an equation might create more solving opportunities, including the possibility of using a Pythagorean identity. All right. So here we have cosine x minus sine x equals 1. and we wish to solve for x between 0 and 2 pi. Let's go ahead and work through this problem. We have an option 2, 1, square each side as written, or 2, add a sin x to each side, then square. Let's choose option 2. So let's go ahead and rewrite it. So if we move the sign over and squared, why are we doing that? Because we want to create a sign squared. Because a sign squared will let us use a Pythagorean identity. All right. The purpose of that will allow us to introduce that 1 minus sine squared. So I can have everything in terms of sine. But on the other side, I was forced to square whatever I had, which was 1 plus sine. And so that gives us all that work. 1 plus 2 sine x plus sine squared x. All right. We go ahead and replace cosine squared with 1 minus sine squared. Now we have to set it equal to 0. So we move our 1 over, so minus 1. We move our sine over, plus sine squared x. And we're left with this, 2 sine x plus 2 sine squared x. We can factor, so it wasn't too bad. We can factor, and we're left with 2 sine x equals 0, and 1 plus sine x equals 0. We solve for each one, and we get x is equal to 0 and 2 and pi, and we're left with x is equal to 3 pi over 2. Because we did this thing, because we squared both sides, we have to be very careful of our answers. Because we did that, we have to check our work. We have to check our answers. That squaring is something you should be careful of. We have 3 possible solutions, 0, pi, and 3 pi over 2. But because these came from a squaring process, it is possible that one or more of them is extraneous. The only way to know is to place each answer in the original equation. So, original equation. So you have to plug it in to your original equation and check. And once we check each one, we see that pi is one of those fake answers. So our only 2 real answers are 0 and 3 pi over 2. Okay, go ahead and try this in class example 9. Now notice it's very similar to our last question. It just wants us to do a different step. So it wants us to square each side of the equation as written. So square here and square here. Actually, don't do that. We'll just go ahead and continue. I don't want to lecture for too long. So let's go ahead and move forward. Okay, we're done. Let's go ahead and do some homework problems before we leave. So before we leave, your homework is all odds. Let's go ahead and try 3. Let's try 3 and let's do one more. 3 and 13. Let's try those 2. And I'll give you 5 minutes. All right, let's go ahead and check our work. Well, let's work it out together. I gave you 5 minutes to give it a try. Let's go ahead and see what happened for these problems. So we want to solve for theta when 0 is between 0 and 360. So this is telling us that we want our answer in degrees. Okay, let's go ahead and work with number 3. Okay, so we see that I have cosine and I have sine. And ideally, I want to be able to have, if possible, the same trig function all across. But I know that cosine squared using a Pythagorean identity would allow us to have only sine, right? And that's what the whole point of it is. So let's go ahead and change it. So we know that, hold on, give me a minute. I just sent you guys an email. I sent you guys an email with a unit circle and a cheat sheet. I really like that cheat sheet with all the identities. All right, so we're going to change our cosine squared using our Pythagorean identities. We know that cosine squared theta is equal to 1 minus sine squared theta So let's make that substitution. So that I have 1 minus sine squared theta minus sine theta minus 1 is equal to 0. All right, we're not multiplying, so we can go ahead and just drop those parentheses. So I have 1 minus sine squared theta minus sine theta minus 1 is equal to 0. All right, let's go ahead and combine like terms. We see that 1 minus 1 adds to be 0, and we're just left with negative sine squared theta minus sine theta equals 0. So let's go ahead and factor a sine. If I factor a sine theta, what am I left with? Well, sine squared divided by sine will just leave a sine theta, a negative sine theta, and we'll have a minus 1. Sine divided by sine gives us 1, equals 0. Let's set each one equal to 0. So that I have sine theta is equal to 0, and negative sine theta minus 1 is equal to 0. We're going to solve for each one separately. All right, so when is sine 0? Well, sine is 0 at 0 and at 180. So theta is equal to 0 and 180. Let's go ahead and solve for theta. So plus 1, negative sine theta is equal to 1 divided by a negative 1. So we're left with sine theta is equal to negative 1. When is sine negative 1? Sine is negative 1 only at 270. I was going to say 180. I was like, that's not right. 270. So lastly, we can say that our answer is theta is equal to 0, 180, and 270. It wants our answers in degrees, and it's just between 0 and 360. So that's all that we need to do. If I would have set all theta in degrees, you would have had to do that plus k ez. Okay, let's move on to number, what's the next one? 13. For 13, 14, and 15, use the squaring technique presented in example 8 to solve these equations. Be sure to check your possible extraneous solutions. So when we square both sides, you know we're going to have extraneous solutions. And usually you're not just throwing out the wolves. There sometimes is a little ending to your question that says, make sure to check your solutions, or something to let you warn you that you're going to have those different types of problems. All right, let's do this one together. All right, now our problem here is that we have a cosine and a sine. And we know that this wouldn't be a problem if we had them in square form. So let's go ahead and square them. So let's go ahead and square both sides. All right, square root of 3 times square root of 3 gives me 3. Sine squared x is equal to, Now I'll do the work on the side. This is 1 minus cosine of x times 1 minus cosine of x. We have to multiply them together. So 1 times 1 is 1. 1 times negative cosine gives me negative cosine of x. Negative cosine times 1, negative cosine of x. Negative cosine times negative cosine gives me positive cosine squared x. All right, so we have that. So we can combine like terms to be 1 minus 2 cosine x plus cosine squared x. So we have, you can write your square first, cosine squared x minus 2 cosine of x plus 1. All right, I see that, hey, I have a sine squared, and I know I can change that sine squared into cosine using my Pythagorean identity, right? So we know that, I'll write the note right here, by Pythagorean identity, we know that sine squared of x is the same as 1 minus cosine squared of x. So let's replace it with 1 cosine squared of x. So that I have 3 times 1 minus cosine squared of x is equal to cosine squared of x minus 2 cosine of x plus 1. All right, now I have all cosines. Cool. All right, I'm left to distribute my 3. So that I have 3 minus 3 cosine squared of x is equal to cosine squared of x minus 2 cosine of x plus 1. All right, we have a quadratic. So let's go ahead and set it equal to 0. So that I have minus 3 plus cosine squared x plus 3 cosine squared x. And now we're left with 0 is equal to 4 cosine squared x minus 2 cosine x minus 2. All right, this is a good point to change it to w's if you want to. So let w equal cosine of x. So we can write this to be 4w squared minus 2w minus 2. All right, 4 times negative 2 is negative 8. My middle term is a negative 2. So what numbers multiply give me 8 but add to give me 2? 4 times 2, I want a negative 2. Let's make that a negative 4. And we're going to place our middle term with. So that I have 4w squared minus 4w plus 2w minus 2. Let's group our first 2 and our last 2 so that we can factor 4w. We're left with w minus 1. Let's factor 2. We're left with a w minus 1. So this factors to be 4w plus 2 and w minus 1. Let's change our w's to cosine. So that we have 4 cosine of x plus 2 is equal to 0. And cosine of x minus 1 is equal to 0. Let's solve. So minus 2, 4 cosine of x is equal to negative 2. Divide by 4, divide by 4. Cosine of x is equal to negative 1 over 4. Simplifies to 1/2. So when is cosine negative 1/2? Let's take a look at a unit circle. Cosine is negative 1/2 in quadrants 2 and 3. Well, cosine is negative in quadrants 2 and 3. So we're left with x is equal to, do we want degrees or radians? We want, I didn't say. I like degrees. All right, so let's write it as 120 degrees and 240. Now for cosine, our other one, let's add 1, add 1. The cosine of x is equal to 1. When is cosine 1? Positive 1. Cosine is only 1 at 0. So x is equal to 0. Those are our answers. So our answers are 0, 120, and 240. But I can't box them yet. I'll just write a check mark. The reason for this is because I have to check my work. I have to check each one and make sure that it's true. And you have to check it to your original equation. So look at the very beginning. What was our original equation? Square root of 3 sine of x is equal to 1 minus cosine of x. All right. So let's go ahead and replace our x with our answers and evaluate at cosine and sine of that value. Let's do the first one. Let's check 0. So we check it when x equals 0. We have square root of 3 times sine at 0 is equal to 1 minus cosine at 0. All right, at 0, sine is 0. So I'm left with square root of 3 times 0 is equal to 1 minus, and cosine at cosine at 0 is 1. All right, square root of 3 times 0 is 0. 1 minus 1 is 0, so that one checks out. Whew, not so bad. So this one checked out. Let's try 120. X is equal to 120. Let's plug it in. I have square root of 3 times sine of 120 degrees is equal to 1 minus cosine at 120 degrees. So we look at unit circle. At 120 degrees, I have negative square root of 1/2, square root of 1/2, negative 1/2, and square root of 3 over 2. So I have square root of 3 times sine at 120 gives me square root of 3 over 2. And I have 1 minus cosine, and cosine at 120 is negative 1/2. All right, let's see what we get. Square root of 3 times square root of 3 gives me 3 over 2. And 1 minus a negative 1/2. Remember to add them if they're opposite signs. So I can think of this as 1 over 1. Get a common denominator, we get 3 over 2. Cool. This one checks off too. All right, let's go ahead and check our last one. 240. 120 worked out. Let's check 240. So if we plug it in, we're left with square root of 3 times sine at 240 is equal to 1 minus cosine at 240. I'm left at square root of 3. Let's take a look at 240. Sine is your y, so sine is negative square root of 3 over 2 is equal to 1 minus cosine at 240 is negative 1/2. All right, if we multiply, I can write it as over 1. I'm left with negative 3 over 2. And then my right-hand side, I have, we add add them, and we're left, you can say it's extraneous. So 240 is our answer. So when we write our actual answer, we want to say x is equal to 0 and 120. 240 isn't a real solution. Now, how do we know that we had to check? We had to check because we did this thing where we squared both sides. Squaring both sides produces a potential extraneous solution. All right, that's all for 6.2 today. Your homework for 6.2 is all odd problems. Before I call it a day, are there any homework questions from the previous homework assignment 6.1 or maybe anything from chapter 5?
The only real question I have is there an assignment up yet? I have a file to turn in, but there's no, as far as I can tell, there's no assignment.
Oh, I'm sorry. I am totally losing track of everything I have to do. I'll write down the assignment right now so that you can turn it in. Thanks.
Yep.
And you also emailed me about the quiz being muted. So I don't know what happened, why it's muted. And I tried unmuting 5.2 quiz and it won't unmute. So I don't know what I'll do. I think I have to go through the process of checking it, which, I mean, you already have a grade for it, but I have to go through the process of checking it, which is nothing too time consuming. And I think from there, I'll let you take it another time.
That's weird because, I mean, it was all automatic before. You posted the quizzes, we took the quizzes, and then it instantly returned the score. And none of this whole you needing to look at it thing. I don't know what the difference
I
is.
don't know. Well, the difference we split the work between professors, as another professor is self teaching this class, and I think they set up so that they have to go through this process.
I see.
So I copied them. I copied this quiz. So in the future, I just won't work with that professor. Alrighty. Is there any other homework questions? No? All right. Well, this was 6.2. It's kind of tricky, so make sure you give it a try. I'm thinking that maybe for 6.3, so that you're not forced to be at one place at a certain time, how about I record a video lecture and I just upload it and you can go ahead and go through it whenever you'd like. How about we do that every so often, just so, I don't know, to give you a bit more liberty.
That works.
All right, cool. Well, that's it for today. I felt really bad for Thursday because I kept you guys for so long. It wasn't my intention, but I did have to go over through that review material for factoring because I know factoring is a big hurdle we have to cross so that chapter 6 makes more sense. So I'm very sorry about class being so long on Thursday. I was so drained afterwards. I can only imagine how tired you were listening to me just talk all the time.
I'm still shaky on the factoring too.
Factoring is not okay. So factoring is something that never goes away, but I hate that when it's taught in another course that they just fly by it because there's so much more to go over, and it's one of those things that just becomes put in the back burner and we never fully accomplish. So maybe I'll upload some videos on some already made ones. So I'll just post a link so you can watch some more on factoring because I know it's just that little thing that's making it so that chapter 6 is just extra hard than it needs to be. So I'll take a look and see what videos I can find that are nice on YouTube about factoring.
I appreciate that.
Yeah.
I never actually took Algebra 2 in high school. I took Algebra 1A and then Algebra 1B, and I don't remember factoring at all as part of that. So this is all new hat for me.
Yeah, but this is why you would take this class with that 136 correct. It's different. And while we can definitely do 3.5 hours together, it's totally different. We're online. I feel like it's worse than being in person because it's more draining. I don't know. I feel like it's more draining, but it totally, you don't have to feel that way too. But I don't know what's going across, what's not. And my hopes are that if you're too shy to ask and if it didn't make sense, that you're making it a point to go through YouTube and look at your lecture again or find some other supplemental material that will help you. But it's difficult. So I'll make sure to make some things available for you guys for factoring other than our review worksheets.
Thank you so much.
You're welcome. Okay, so I know you're all there with your dark screen and your mic off, which is fine. I don't mind. Have a nice day. I'll see you on Tuesday. I'll
All right,
post a recorded video for Thursday. All
sounds
right.
good. Take care.
Thank you. Thank you. Have a nice day.